y'all. Tonight, I'm excited for a chat about space travel with Dr. Vandy and Dr. Ben. So sit back, buckle up, and let's get to the sunny spot on Skeptic Haven.
Jefferson laid great stress on it. It wasn't enough, he said, to enshrine some rights in a Constitution or a Bill of Rights. The people had to be educated, and they had to practice their skepticism and their education. Otherwise, we don't run the government. The government runs us.
Good afternoon, good evening, wherever your time is to everyone. Thank you so much for joining us on the Sunny Spot. I would like to welcome two wonderful people, Dr. Vandy and Dr. Ben. How have you two been? Ben.
I've been hanging in there.
Great. And you, Vandy?
I've been good. It's been a good summer. I went to some conferences and had a great time doing that. And it was my first time actually visiting England. So yeah, it's been good.
Awesome. Fantastic. What have you been doing this summer, Dr. Ben?
Oh, well, I don't know about the summer, but spring we went to Ireland and Scotland. And so I'm still kind of recuperating from that.
Well, I'm just living here jealous. So I've not been anywhere. Well, I've been traveling for work, but nothing like Ireland, Scotland, or England. Can I just fit in y'all's suitcase and go with y'all to your places? Because that would be really cool.
Works for me.
So I've been following the Sarah Boone trial. She's a woman in Florida who put her boyfriend in a suitcase and now he's dead. So you probably don't want to do that.
You are so right. I haven't followed it, but I see it every little bit here and there. And I saw the video of her being arrested, when they came to the house when she made the call, and it was some crazy stuff right there. Yeah, okay, never mind. No suitcases. No suitcases. All right, so tonight I'm really excited because we're talking about what space travel will be like. And I think all of us would love to know. I will tell you that as a Trekkie, I am dying for us to get to the point where we can be on the Enterprise and go to strange new worlds. So are we going to be able to go to strange new worlds?
What do you think, Vandy? You going to be the one to disappoint her or me?
Well, it depends on what you mean by strange new worlds. I mean, I think that the moon and Mars are strange new worlds. We're definitely going there.
Okay.
And nearby, with current understanding of physics, visiting nearby stars on decadal or more of centuries, millennia timescales is possible. But we are going to have to figure out some more fundamental stuff if we're going to be zooming around at warp 9. The idea of warp drive is based on some stuff that's not total nonsense, but it's very much still science fiction.
Okay.
Which stuff is not total nonsense?
The idea that you can do the idea of sort of scrunching chunks of space and then
the Albuquerque drive. Yeah,
exactly. I didn't want to try and say the name because I don't have that amount of self-confidence.
Okay.
I figured I'd just murder it. It would be okay.
Okay, so Wes has a quick question before we really dive in, so I thought I'd go ahead and pop it up. He says he wants to know what you think of using nuclear power to space travel, or to travel in space. Would that give us the power to do that? Great question, Wes.
Man, don't ask a nuclear physicist a question like that. We'll spend the whole hour talking about that.
Well, I can narrow it down. So let me narrow it down for you, Dr. Ben. So I can think of a few different ways in which this could be meant. So there's the sort of caveman approach of using nuclear power, which is you get a big shield behind your spaceship and then you literally detonate nukes to launch yourself. And then there is the other idea, which is basically you use a nuclear power source in some way to drive an ion engine or something like that for a very long time at very low acceleration.
So the first thing is called an Orion drive. I'm trying. Was it Dyson that came up with the idea of the Orion drive, sort of credited with it? I think it was somebody like that. The other thing, where you heat up a bunch of gas in a nuclear reactor and then shoot the hot gas out the back end, is called a Nerva engine. They actually did that. It's actually a thing. I mean, they never tested it in space, but they actually, you can find old videos from the 50s where they had actually developed the Nerva engine, measured its impulse, know what it's capable of doing, know that they could have done it had there been the political will to do it at the time. So it's a thing, and it's a real thing, and it has a very impressive impulse associated with it. I think the estimates I've heard on that are something like 0.3 or 3% the speed of light, not 0.3, that'd be 30%, but 3% the speed of light, which is damn fast compared to like chemical rockets. I mean, that's the closest real technology that anybody's ever come up with that even approaches something close to light speed.
Oh, that's cool. So Al Trucker had a great one because I'm wondering about this. I want to know how we can harness, or can we even harness the potential energy of a black hole to aim our way around the galaxy as a scaled up version of the way we use solar system gravitational mechanics too.
We would have to find a black hole near enough by to be useful. So the way that the solar system is so useful in space travel is that you can basically shoot it off, and then as the planet is orbiting, you sort of catch up to it, and then you get slingshotted and you end up getting more energy than you get out, because basically what you do is you go into the gravity well, and then while you're in the gravity well, you accelerate. Like, that's where you turn on the rockets again. And it turns out that you get a big net positive, and the consequence is that the planet slows down in imperceptible amount. But it also very much limits basically scheduling, because you can only do that when the planets are lined up well enough to do it. And it's why, like, the Voyager probes had to be launched at pretty specific times, or else their whole trajectory path schedule through the solar system just wasn't going to work. So we'd need to find a nearby black hole. And I'm not sure we want to find a nearby black hole that much.
Yeah, it would be helpful if it was nearby and in orbit around the sun, then maybe we could do something with that, right?
Yeah, but then we have a black hole in the solar system, which is
then there would be a major
ideal
hazard in the solar system that we'd have to navigate around now.
Well, let me ask you this: is it possible that a black hole is kind of a
wormhole?
What?
Is
yeah,
what
like a
asking?
wormhole. Yeah, could it actually link to another place in the universe, or maybe another universe entirely?
I mean, it's postulated that it could. I wouldn't want to be the first guy to jump into the black hole and find out. Particularly, just the tidal, when the tidal forces spaghettify me before I can even get through the wormhole to find out if it goes anywhere. That would be kind of sucky.
That would be bad. I think so too.
And
well,
I would expect
that straw sucky, actually.
I would also expect that if there is actually like a wormhole sort of tunnel thing, I would expect that it is probably very, very small. so that even if you didn't get ripped apart and spaghettified by the tidal forces, you wouldn't be able to fit through it, because it would be like the size of a subatomic particle or something. But
Okay.
Who knows?
And then you'd pop out in a white fountain, and you'd have to deal with all the radiation surrounding you. So you'd have lots of mundane things you'd have to deal with to go along with this, really cool way of getting from one end of the universe to the other.
Okay, so I tell you what, this topic is just making people ask questions left and right. But before I go on to any others, I want to know from you guys, are we going to be able to do any space travel at all? I mean, I know we've talked about actually being, being like the Star Trek and all of that. But besides what we've already done, which is, basically going to the moon, are we going to be able to travel further than that? And if so, when?
We will be able to, we will land on Mars in my lifetime, unless I die we'll land on Mars in all of our lifetimes, unless we all die prematurely. I think it's going to happen in the next 15 years.
Okay.
Maybe that's optimistic, but I don't think it's.
Well, Elon's throwing a lot of money at it, so I don't know whether that's optimistic or not. It's certainly doable from a technical point of view. It's doable.
Yeah, and SpaceX has, like, the technology that they're sort of going and building as far as that goal goes. I have found their progress over the last 2 decades quite impressive. They don't have the same amount of kind of unified huge effort that really only existed in the United States in the 60s, when like NASA was receiving something like 4% of the entire budget or some hot nonsense like that. Elon is a billionaire, but he's not a trillionaire. So it's a lot. Beyond the solar system, though, and once you get, like, Mars is tough. Moons of Jupiter are tougher, but they're not like an order of magnitude tougher. They're like maybe twice as tough. And the biggest problems, I think, are actually psychological.
Okay.
I don't think that the biggest problems with that sort of level of space travel are, like, the biggest fundamental problems are technological or astrophysical. I think it's that there are a lot of negative physical and psychological effects from being in microgravity and zero G, and from being isolated, and from being cooped up in a small group of people. And it's like, I was on in grad school, a good chunk of my salary was paid by a NASA grant, because we were putting a small little rack-sized cold atom machine up on the ISS. And my advisor was telling me all about how he would sit down at these NASA meetings, and most of the people are not doing, finicky physics experiments. Most of it's like biology and a lot of psychology experiments. And the hit that you get, just like the sort of baseline hit that you get to basic cognitive function, is actually apparently rather significant. Like, people are simply, their brains don't work as well. It's for a lot of reasons. So I think that's, yeah.
And it's still expensive. It's still something like, what, $4,000 a pound to put something in low Earth orbit.
Yeah.
And it's not just the person, it's all of the food that person is going to have to carry with them, and all of the supporting environment that's going to have to go with them. And that's low Earth orbit. That's not actually getting to escape velocity and traveling 6 months through the depths of space to get to some other planet like Mars. So it's an expensive proposition, to be sure.
Okay.
Yeah.
Okay, so that has. Do you guys know I can't think of the name of the show, but Oh my gosh, it was so good. It had the Belters, the
you're thinking about The Expanse?
The Expanse, yes.
I haven't seen it or read it, actually.
Oh my gosh.
I know, I'm so sorry.
It's so good.
It's funny. I tried to watch it. I think I even got through the whole first season. A lot of my engineering friends, when it first came out, was all excited about it, and it just didn't resonate with me. I mean, I know plenty of people that thought it was wonderful and all that, but something about it just didn't hold my interest. I enjoyed, the Isaac Asimov thing that Apple TV did, Foundation series. Better, much better than the thing you're talking about.
The thing about it that I wondered was if we are able to go to Mars and actually make it livable in some way, and then people start living up there, would they actually kind of change in such a way that we would have people who, the people who live on Mars would be kind of their own different species? People?
They would have
species. I mean, they would be isolated, so they would definitely evolve.
They would. It's an whether or not there would be enough breeding, but for one thing, it would take a long time of isolation for those things to actually become really significant and non-cosmetic. Like, you could have a lot of cosmetic things, but to actually speciate and become incapable of interbreeding, that seems a little bit unlikely, because you would still have interbreeding. I think it wouldn't be completely separated in that sense. Mm-hmm. And it would operate at long time scales. I think a much more directly relevant issue is that it is absurd to imagine that you could have political unity. Like, a self-sustaining population on Mars is not going to be part of any Earth country after a couple generations. I mean, the first time somebody's born on Mars, that person is a Martian. They're not an Earthling, and it is absurd to think that they would have to identify
it's crazy to think about it. It's really crazy to think about. So in any talk about space travel, if it's any distance, and if it's any length of time, beyond a lifetime, it's going to raise a whole lot of different questions and issues that I don't know that we have all thought about necessarily.
Well, we talk about this when when I do the cons and stuff, and my wife's a psychologist, and so she has just now started giving talks, or at least being on panels. She hasn't done a singleton talk yet, but she's starting to sort of, just get into these discussions about the psychology of being on a generational spaceship. And it's going to be rough. And the last panel she was on, it was interesting because they got into the conversations about infants and teenagers, and how teenagers always wander around and get into stuff and deliberately try to be destructive. And so, I had visions of this, huge, monstrously huge ship where all of the young people were at the core of the ship, were away from the engines and away from anything dangerous, the shielding, all of that stuff. And they were only allowed to sort of move out from the core of that ship as they got older and mature enough and trained on how to handle certain systems, So it really it becomes this huge security issue where people can't just wander out, that can't get bored one day and wander out into the woods and start, grabbing tree limbs, or in this case, wires, and seeing what would do if they, yanked them out. And couple that with the fact that they would be incredibly bored, right? There would be this urge to get out and to see other things, because you've grown up in this room that, if you're lucky, is the size of maybe a missile silo, say
Yeah.
10,000 square feet, right? And so 10,000 square feet becomes awfully small, if you're stuck in that type of area for the first 10 years of your life. So
yeah, that would not be good at all.
It gets tough in a lot of ways, from the psychological aspects of it. It just keeping somebody from going nuts and doing something stupid. Even the adults that have been trained to work on whatever subsystems they're supposed to work on. There have been books that have written about people going into open rebellion because they're on this generational ship, and they were born on this ship, and they never signed up for this. And so they're not having fun. They want to go back to Earth, and they were born there. They never signed up for this, so they're like, no, turn this thing around and go back. Which, of course, simple momentum's going to stop them from being able to do that. And then what do? You overthrow the government on the ship, and then you do what? Sit around and have parties all day long until you drink yourself to death, or what? Because what else can you do? You're stuck on this ship heading towards this star, and you literally don't have the fuel to turn around and go back. So you can hate it, but there's not a whole hell of a lot you can do about it either.
Yeah. Okay, so that's interesting. Yes, those are great topics to think about.
Oh, yeah, we could do a whole hour just on any of that kind of stuff.
I know.
We'd have to get Annie in here to really talk about the psychology of it, though.
That's blowing my mind. And that's my field. So now I'm really starting to think about some of the neuroses that you would have in the adults, let alone these kids. And the thought of saying, I didn't sign up for this and I want to go back, but back where they've never known. I mean, just all of that.
And a world that wouldn't know them, they wouldn't know and wouldn't know them if they could go back.
Yep. Wow. That's crazy. That's crazy to think about. So you had mentioned Elon Musk a little bit ago, and Jesus Tales did have a question, so I thought I'd bring that up. Given a few $1 billion in a couple of decades, could Elon Musk duplicate those Nerva engines of the 1950s? You guys kind of spoke about this, but...
Yeah, of course he could. I mean, if they could develop the technology and prove that it worked in the 50s, and it was not like a super well-funded program even then, it was probably the equivalent of, let's say, $100 million, even when they did it the first time around. It's because it's not like it was some huge mega project, it was just, hey, if we tried this, would it work? Oh, look, it works. So yeah, absolutely he could do it. The next trick would, of course, be launching it into space. But he's already demonstrated that he's got the resources to do that. The problem you're going to run into is all of the environmentalists losing their mind, over the whole thing.
Exactly.
It's just like even now, there's a whole lot of issues when you start talking about putting nuclear batteries on probes, on space probes. And we're not even talking about people being on the ship or anything like that. It's just, there's always some hand wringer going, what if a rocket blows up on the pad and it spreads radiation everywhere? Which, of course, it's a whole other discussion. We don't have to get into that, but it's like,
believe it or not, we can do the math on that.
There's uranium in the ground now. Where do you think we got it from? We concentrated it so we could do things with it. And if you blow it up and spread it all out over the surface of the earth, then it's probably not going to have that much of an impact.
Especially if you're launching from a place like Florida. Because if it, unless it's like right down at the bottom, if it's any decently high up when it explodes, the wind is going to keep it away from humans and disperse it enough that like you're probably just not going to see much of an effect. Unless it's a lot of radioactive material.
This is a different topic, and I don't necessarily want to discuss it. It's not a fun topic for me to discuss, but a lot of what limits us now is the hand wringers going, what about this? What about that? And they're usually not even scientists that are doing it.
Right.
Yeah. There are very few scientists who are on the whole skeptics of or disagreeing anti-nuclear power.
Yeah.
All the scientists I know are pro-nuclear power, because it's just very clearly the cheapest and safest option.
And engineers.
Yeah.
Mm-hmm. Anybody technical that has looked at the numbers, and they're just really trying to answer the question about what are we going to have to do to survive on this planet and deal with the greenhouse problem that most of us agree is a problem now. And nuclear power is the only solution that works. You don't have to like it, just like you don't have to like fossil fuels. They're dirty, and nobody really wants to handle them and dig them out of the ground and all that. But it's the only thing you've got in modern day technology that's going to solve the problem for you in the short term.
Mm-hmm.
So Wes asked a great question. Did you ever calculate the relativity how long it would take to travel to another solar system that could have a planet viable for human life? Let's say it's really, really close, like 100 light years.
Now he's just baiting us. He knows that we've done those kinds of calculations.
Have you and I done them? So if you accelerate at 1g, it turns out that you become substantially relativistic after about a year of that. So like after 10 years of sort of onboard ship time, you're going at a very, very high fraction of the speed of light. The question is, how do you accelerate for 10 years at 1g? Don't ask me questions I'm not prepared to answer.
We can. I have slides. I do the cons and presentations.
I love that. I love it.
I could bury you guys in slides with calculations if that's what you really wanted. But I kind of wanted to start off a different way 27 minutes ago when we got into the relativity discussion, and you guys are going to think I've gone way off on a tangent, and it's like, where the hell is he going with this? But I kind of want to set a frame for this discussion.
Okay.
So I was teaching, I don't even think it was electronics. I think I was teaching physics, general physics, a few months back. And I was talking to my students about electrons flowing through a wire. And it's like, how fast do the electrons flow through the wire? And they're like, well, it goes at the speed of light. You flip the switch, the light bulb comes up. And it's like, no, the electrons go at like 1 millimeter per second. And they're like, how's that? And so I said, okay, imagine that you have a big pipe that runs from New York to Los Angeles, and it's filled with billiard balls. And so you want to signal your friend in Los Angeles that, you're there or whatever. And so you push a billiard ball in here at New York, and a billiard ball pops out in Los Angeles. And it's not the same billiard ball, right? So the impulse travels, the information travels instantaneously, or does it?
It
actually travels, that information actually travels at the speed of light.
In that context, it would be at the speed of sound, I think, of billiard balls.
Don't split hairs with me about air in the atmosphere and that kind of. It's an evacuated pipe, okay, and it's frictionless and blah 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 and all that. The pulse still travels at the speed of light, and then you have to ask, why does the pulse travel at the speed of light? If I shove the billiard ball in over here, why does it take that much time for it to propagate from New York to LA? Well, stop and think about that for a minute. You push this billiard ball, and its nearest neighbor doesn't know that billiard ball has moved for some amount of time. That amount of time before it feels that electric field of its neighboring atoms change and get stronger is the speed of light. So you're actually compressing that whole line of billiard balls because this billiard ball on this end doesn't know to even get out of the way of the billiard ball that you're shoving on the other end. So now when we talk about spacecraft and all the weird effects that happen in relativity, it's the fact that the front of the spaceship can't get out of the way of the back of the spaceship when you try to accelerate at anything close to the speed of light. This thing becomes this wall in front of your engines, if you will, that the atoms don't know they have to get out of the way. And they become this thing that just can't move out of the way fast enough to go any faster than that. And so that sets the whole time, the whole framework for this faster than light travel business. I mean, that's really what the problem is.
That's a great way of putting it. Hadn't even thought of that.
And the speed of light fundamentally, it's a little unfortunate that it's known as the speed of light. It's really the speed of causality.
Yep.
It's the speed of information propagation. But I think speed of causality is a sort of more, it's an easier way of thinking about it.
And it's funny, when I was an undergrad, I mean, I can remember being, a kid and the professors, we'd run up against something like this. And the professors would always say, well, that signal only travels at the speed of light. And so they'd tell me there was a limit there, but they never explained why that limit was there. So that's why I like that analogy so much, and have used it now on several occasions. Because I thought I was just being brilliant when I came up with that. So
You were. That is honestly a great way of thinking about it. That's the best way. I've never really understood why there was a limit. Just that, okay, we can't get faster than the speed of light. Okay, why? I don't know.
And every now and then you'll hear somebody say, well, we thought the speed of sound was a limit, blah, blah. And no. No physicist ever told you that, right? Ernst Mach understood that you could break the speed of sound in the 1800s.
Right.
That's why Mach speed is named after him. They knew that cannonballs and all kinds of things go faster than the speed of sound. So no serious physicist ever thought that the speed of sound was the same as the limits applied by the speed of light. That's two completely different things.
Yeah, that makes sense. So I did not feel like you took us off in some weird wonderland, just so you know. You were not.
I tried to do it as quickly as I could. I didn't want to sit there and pontificate for 10 minutes, without somebody getting to say anything.
There is one thing about what you said that I think I always find confusing whenever I actually sit down and sort of do work through problems in relativity, which is I find relativity to be much more mind-bending and confusing than quantum mechanics. Part of that is because I've spent a lot more time doing quantum mechanics, but also because I don't have the same ingrained pre-existing intuitions that you do with like imagining objects just moving. But you think if you just dial up the speed, like length contraction, time dilation, these are weird. These are very weird things, and your intuitions about how things move in everyday life just categorically do not bring you to the correct answer. You have to think about them more carefully. And one of the ways that manifests is that if you're on a spaceship and you're accelerating, and we watch you, and we watch you from a stationary outside observation point, and you start at zero velocity, and then after some amount of time, you're at 99% of the speed of light. We see that you're coming up against that wall. You can't go faster. You can't because you can't move faster than causality. But the person on the spaceship, they will keep on experiencing an acceleration. They'll just notice that everything else sort of seems to stop. The universe sort of stops accelerating backwards, but they keep on accelerating. Like if they put something stationary outside, they would keep on accelerating with respect to that stationary object, which is not accelerating because it doesn't have any engines. If they started at 1g and they kept on accelerating at 1g, they would always notice that if they put a thing outside and let go so that it remained at a constant velocity and they kept accelerating, they would always measure their acceleration to be at 1g, even though the other people are measuring, like they're up at 0.99 times the speed of light, and then 0.99, and but those two things, and it's because special relativity screws up time and space in all sorts of funky ways.
That was fabulous. That was fabulous. You looked so sad when you said it too.
Damn it, we can't go anywhere.
Yeah. Well, it really is. Sometimes people ask the question, why is the speed of light so fast? I think when you actually look at like cosmology and astrophysics, I think a much, much more obvious question is, why is it so darn slow? Because the nearest star other than the sun is a little less than 4 light years away. It takes the fastest thing in the universe almost 4 years to get to the closest other like big thing. That's not very fast. Like, imagine if it took 20 seconds for nerve signals from your feet to reach your brain. That'd be really weird, and everything would be messed up.
Yet, if you were a giant the size of the solar system, that would be what happened. Right?
Yeah.
And you'd live on a time scale. You would experience time in a different way. You'd live on a time scale where you wouldn't really think that was a problem. The problem with all of this stuff, whether you're talking about quantum mechanics or whether you're talking about special or general relativity, is we grow up in a certain environment and we have an intuition for that environment. But we don't have any kind of intuition for moving it near the speed of light and what life would be like that if we did that, or the really small, like in the quantum world. So it's not surprising that the laws of physics are actually different, in those situations, and it's uncomfortable to us because we have no experience to draw from that.
Right.
So the fact that it kind of works and it makes us uncomfortable doesn't necessarily mean there's a problem with it,
Right. Yeah.
I did pull up a slide if we don't want Wes to feel cheated.
Okay.
We could throw that up if we wanted to.
Oh, that's a good idea.
That's a great idea.
I used a very simple, let's see, how do we do this? I forget how we do this. Oh, wait. I'm going to go to slideshow so that we can actually see the slide on full scale. And then I'm going to go here where it says present. And it says share screen. Yeah. Share screen. Yeah, I could do that. And I think Chrome tab, Windows, that window's the one I won't share.
All right, let me get that up, put it on.
There we go. So this is from my relativity talk, right? And obviously we're using a gamma factor equals to 2. So that's a speed of 0.866, the speed of light. And we are talking about a spaceship going to Alpha Centauri, right? Or Proxima Centauri, whatever we're calling it these days, right? So if we click this slide, there's a few notes here. So what happens is you're moving at almost 90% the speed of light. For somebody watching you travel from the Earth to Alpha Centauri, it looks like 4.97 years go by. The actual length is 4.3 light years. So it takes you 5 years to get there, right? If you're on the spaceship, all your clocks slow down. And so you think 2.5 years have gone by, half the time. And so it's like, how does that work? Oh. What happens is as you approach the speed of light, the universe shrinks. And so Alpha Centauri doesn't look like it's 4.3 light years away if you're on the ship. It looks like it's only 2.15 light years. And so it makes perfect sense to you that the speed of light is still the universal speed limit, and you're traveling 2.5 years to get to something that's 2.15 light years away. All perfectly reasonable. And if you're somebody on the outside watching, and it takes them 5 years to get there, going at 90% the speed of light, seems perfectly reasonable to that person too, because from their point of view, they have to traverse 4.3 light years. And so all of this is required for this to be logically consistent. Time has to slow down and lengths have to contract. So there's some numbers for you. Hope Wes is happy.
Thank you, Wes. Okay. Time slows down.
What that means is that locally, time always is moving locally for you at 1 second per second, which is an annoying sort of convention. But right. But what we mean by when we say that time slows down for the moving thing, we mean is that if you had an observer observing, and the word observe does not actually mean like what you would see if you would look at it, because there's a bunch of other geometrical effects that end up happening because of how space is bending. But if you had, if you put a bunch of clocks, you synchronize clocks, and then you put them with that person, they did the experiment, and the person that's moving wrote down the time that they see on their clock when various things happen. And then at the end of the day, you're comparing those two pieces of paper, showing what your clock said and what their clock said. Then you would see that their clock had fewer ticks in between two events that you could, like, if they went out and they came back and you're both standing there comparing your piece of paper, you're clearly right there together at the same time, at the same place, but they have experienced less time that has elapsed. That is the twin paradox, the one where they go out and then they come back.
Yep.
But locally, you will never perceive this changing locally, because you are always at rest with respect to your reference frame.
Yeah. Well, what looks weird to you locally is the whole friggin' universe shrinking around you.
And the universe that's coming at you turns incredibly blue. The universe behind you turns red. It's all sort of scrunching. Objects that, like if you look at a cube from the side, or if a cube passes you, and a cube passes you at higher and higher chunks of the speed of light, one, it's going to like change colors. You're going to get like huge Doppler shift. It's going to be really obvious. That's more straightforward to understand. The other thing is that you will see parts of the cube that geometrically, when it's moving slower, you simply cannot see. You can see like the back of it sometimes. It's very weird. I think it's called the Penrose effect.
Yeah.
I might have be able to find a video.
That's so cool.
And it's not a trick of mechanical clocks or, biology or anything. When time slows down for you, your heart rate slows down. To an outside observer, everything still feels the same to you.
Mm-hmm.
But your heart rate slows down, your clocks tick slower. If it's a digital clock and it's electronic, it slows down. And so, or the thing I like to do, because we live in a more modern world now, right? Streaming video. It's like if you actually had a streaming video from the spaceship to the Earth, and you were talking to your friend would think something seriously wrong had happened to you, because you'd literally be communicating with your friend at this really slow speed, at half speed. That's the Doppler shift, right? The thing that's funny about that, of course, is he thinks you're talking slow, and then it takes a while for his signal to catch up to you, so you think he's talking slow too. So both of you are talking in slow motion in that case. Both of you think you're crazy because neither one of you are talking fast enough.
And see, that's weird to me because I would think that the other one would sound like it's talking fast.
That's the
Instead of
relativity
both of
part of
them.
it, right? Because you could say you're a spaceship going off at 9/10 the speed of light in this direction, or you could say from the reference point of the spaceship that you're sitting still and the Earth's just receding from you at 9/10 the speed of light. Who's right?
You're both right.
And Einstein says you're both right.
So this is what I was. This is what I was talking about. It's called the Teller-Penrose effect, or Terrell. Sorry, not Teller. Terrell rotation. So an object is moving towards you at relativistic speeds, can have its backside be visible while it's still approaching. So the backside of this cube is red. The cube is going past you 1 kilometer overhead. I don't know how big the cube is. Probably like a kilometer large or something. And when it's very far away coming towards you, you can't see the back of it. You can only see it when it goes right overhead. And it doesn't. The one thing that's bad about this animation is it doesn't tell you when it's overhead. I think that it ends when the cube is actually directly overhead, which is the first time you would be able to see the backside of it if it's moving at reasonable God-fearing speeds. But when you decide to go really fast, the universe decides to just get all bendy, wendy, timey-wimey, and the other thing is, this is a cube. Does it look like a cube?
Mm-mm.
This is what you would see. It is not what you would observe. It is not what you would measure if you did the process of putting a local clock and a local measuring rod at every sort of point in space, and then have everybody doing their measurements locally. And then when everything's done, you come together and compare your notes on your pieces of paper, and then you describe what's happening. Because what you see with your eyes is not a measurement of what's happening locally over there. It's a measurement of what's happening locally at your eyes, which is getting contributions from a bunch of different stuff that in the reference frame of the cube are not happening at the same time. It all comes down to the idea that you cannot synchronize clocks. And anytime you are doing anything that requires intuition about how things move, you're fundamentally assuming that time is clicking the same way everywhere, and that things that happen at the same time happen at the same time. And that all breaks.
Wow.
And these are just speed effects, right? So and you have similar effects with gravity.
Yeah.
So you jump in the black hole and you hope to go through this wormhole, to get to some other part of the universe. The only problem is time comes to a stop for you as you approach the center of that wormhole.
Yeah.
Singularity. So gravity slows down time too.
Yes.
So Jesus Tales has and I know there's other questions, guys. I will get to you guys, but this one.
Well, this is obviously a hot topic. This should be the thing we discuss all the time.
Exactly, because I'll tell you what, this is making people's brains kind of expand in weird ways. You can see the back of their brain before they pass by. If a spaceship...
Yeah,
it's physics. That's why physics is fun.
It is, isn't it? If a spaceship traveling at 99% the speed of light turned on a flashlight, how fast would that beam of light travel?
See, this is why we have to have all of these strange effects and why we had to have this conversation. So if you're in the car going 99% the speed of light and you turn the headlights on, what do you see? You see the headlights project light in front of you at the speed of light, because space has shrunk and time has slowed down. So it still looks like the beam of light is traveling away from you at the speed of light. You can measure the speed of light in any reference frame you want, and it's still going to read 186,282 miles per second.
Yeah.
That's
a person
the whole premise of special relativity.
And you, as when you're in that car going 99% the speed of light, you are in essence not moving at all as far as the beam of light when it starts.
Yeah. The speed of light's just screaming away from you. The light is just screaming away from you at the same speed it would seem to scream away from you if you were just on the Earth doing the same thing.
Yeah. So comment about that analogy. Dr. Ben, what is wrong with you? The canonical example is to use a train. Okay. Did you never read Einstein's papers?
I know Einstein loved trains. He was like Sheldon in that regard.
Well, trains also, I think trains, because the thing is, when you're on a train, if it's a smooth train, you can't tell you're moving. If it's a smooth ride, which at low speeds it very often is. I have had so many times when suddenly I look out and something's moving and I get a weird like vertigo sort of thing because my brain is like, I can't tell if I'm moving or if that's moving because both of these things look big enough that they shouldn't be moving without it being obvious to my monkey brain. And
now, what kind of train were you on at the time?
Yeah.
I figure I'm going to get him into Sheldon mode, and he's going to tell us about the type.
I don't know about trains.
The type of cars, and how they're coupled together, and all that.
It was the London Underground. So, but only certain parts of it, because most of the time it's clickety clack. Once it's starting, but
my dad was a pilot, so if I wanted to go there, I'd talk about planes. Which got smooth air. That's real easy.
So you on the train flashing a flashlight ahead of you or behind you or to the side, you're always going to see that move if the train is not accelerating. Even if the train is accelerating, you will always see it moving at the speed of light. But if it's accelerating, it'll start bending too. But let's assume the train is not accelerating. You always see it moving away at the speed of light. The person sitting off on the station, watching you do all these things, wondering why you're standing on a train, flashing flashlights, especially, it seems very dangerous. It's moving at the speed of light almost. They will see also that it is moving at the speed of light, but not relative to you, relative to them. So they will see if it's like one of those, if it's a pulsed flashlight, like that you use to like flash in the eyes of burglars and stuff. I don't know. Then if you shine one in front of you, they're going to see those pulses sort of going away from you only kind of slowly, and the pulses that you're sending backward going away from you almost at twice the speed of light with respect to where your position is. But in their frame, everything is moving again at the speed of light, assuming it's all in a vacuum.
Isn't that fun?
Yeah, it's messed up.
That's very messed up.
It's so and
we haven't even talked about the other thing that Einstein loved to think about was simultaneity, right? Yeah. So you're on a train and two lightning bolts hit the ground, and if you're standing on the platform, you see the two lightning bolts hit the ground at the same time. But if you're in the train, the lightning bolts aren't simultaneous. One hits the ground first and one hits the ground at some later time.
Okay, now I want to know what in the world that is. Why would you see that in two different ways? Just because one you're on?
That's pretty simple, because if you're on the platform and you're not moving with respect to the ground, you see the two lightning bolts come down. They're equal distance. Okay, but if you're on the train that's moving, even if it's crossing the platform when the lightning strikes, what's going to happen is the train's going to move some. So this lightning bolt, the train sort of moving toward it. This other lightning bolt, the train sort of moving away from it. So it takes the light an extra millisecond or whatever from the more distant lightning bolt to actually come into the window of the train.
Okay, I get it. That makes sense.
So that's one of those easy things, but it's the thought experiment. One of the thought experiments he did when he was trying to explain relativity. So things that seem simultaneous in one frame of reference are not simultaneous in another frame of reference.
Yes.
It's interesting. I keep hearing the words, it's all about perception. We think about that for every other thing. And now this, like, perception is the key to everything, I guess.
You're getting all psychological on us now.
I know. I can't help it. That's what I do. Y'all are all mathing on me, and I'm doing the,
But I'm gonna split hairs with you. It's not a perception thing here. It's not that your brain's doing something different. It's that physically this is what's really happening, right?
Right. Yeah.
So yeah, your perception is different, but it's different because in your physical world, that's what happened in your physical world, your frame of reference.
Mm-hmm. And you guys all have to take it out from the psychological and to put it into math. You're absolutely right. I'm just picking on you. So okay,
we can start talking about doing drugs, and we can talk about psychological stuff and all the things that happen there too.
That is true. I would love that conversation. So Al Trucker earlier, this has been a little while since he posted this, but I wanted to hurry up and get back to some of those questions that everybody had. Is the speed of sound a factor in every low? I think he's meaning every low pressure system.
I'm trying to think, what's the horses got to do with anything?
Very low pressure. I think very instead of every, but yeah.
Okay, good.
In every
now at least I'm tracking again.
I'm going to start over. Is the speed of sound a factor in every low pressure system, like the area betwixt matter that is clustered? I just like the way Al Trucker talks or writes.
Yes. I think the answer to that question is yes.
Yeah. I appreciate
propagates differently depending on what type of system you're talking about. Whether it's gas or solids or liquids or, how close the atoms are together. So I think the answer to that question is yes, if I understand what he's asking.
It's so if you're talking about the propagation of this is going to be circular. If you're talking about the propagation of an audio signal or a sound wave, then it's going to be the speed of sound that determines that. And that is because ultimately you have atoms that are responding to the electric and magnetic fields of other nearby atoms. And those atoms all have kind of mass and stuff. So it starts feeling this electric field, but it doesn't actually, it's a massive thing. So it has to accelerate before it starts getting close enough to the next one that it starts to push on that one. And that's why you'll have things, why the speed of sound is different than the speed of light. And so I very much appreciate Al's question because it lets me once again say, well, actually, your earlier comment about the billiard balls, it would have moved at the speed of sound. I maintain this point.
Okay. They would move at the sound in some media, though, that wouldn't be like air. They wouldn't be. It would be
the speed of sound in the billiard balls.
It would be an effective media for whatever the billiard balls were, ceramic or whatever, but not actually ceramic as a solid piece, but something. Yeah. Something between air and ceramic.
Okay, Wes had a question earlier. His is actually in two parts. I'm going to show the first part and then the second. I've always thought that the faster something is, the heavier it gets, and therefore needs even more power to propel it. Is that correct? And that's part of why there's a limit too, right? I'm going to go back to
God! See, we forgot about the mass effects, but yes, that is correct. Things, and it's that the fact that there's this wall of matter in front of you, right? That doesn't know to get out of the way as you get closer and closer to the speed of light. So you can view that as you being more massive. You feeling like momentum's a lot harder to overcome. Right, which is how we generally define mass, right? We define it in terms of momentum and being able to accelerate something. But yes, there are mass. The short answer is yes, there are mass effects too, where your relativistic mass goes up as you start to move faster.
there is a really cool experiment. It's like an ion trap experiment that some group in Florida, I think I can't remember what university they're at, but they do very, very like fine measurements of how fast basically like electrons can go around an atom. So it's an ion, so there's like an extra electron or something, and if the electron is in a higher energy state, it's kind of moving at a different velocity, and that you can predict how fast it would move around if it didn't, or if it did have these mass effects. And you see that it actually gets heavier as it moves around, and it's a very subtle effect, and they have to basically sit and look at one atom over the course of multiple weeks and months, and sort of track how fast stuff is moving around. It's crazy. But things in that sort of sense do kind of become like heavier. This is also the case but it's also true in other ways, and it might actually be mostly in effect due to binding energy. If you add a bunch of particles together, their total weight is different from the combined weight of each individual one. And it can be less or it can be more, depending on if it releases energy or requires energy to create this composite thing out of the particles. But this is why it releases energy when you break apart heavy atoms, and why it releases energy when you break apart heavy atoms, and why it releases energy when you combine light atoms. Because it turns out that in one case 1 + 1 equals a little bit less than 2, and in one case 2 equals a little bit more than 1 + 1.
So you're saying that the relativistic mass goes up as you combine nuclei together and they orbit around each other faster?
It does until you get to iron, or it goes down. Iron is at the peak of the binding energy curve.
Mm-hmm. Yes.
So if you want to start combining atoms, then when you get to iron, you're going to be left at the end of the day with less energy than you put into it, which is why stars do not produce energy net when they're fusing heavier things than iron, which is why they collapse once they start doing that sort of thing. Because
I love that you're explaining mass defect to the nuclear astrophysicists.
I'm not explaining it to you. I'm explaining it to the audience.
Hey, I'm here too, and I'm not an astrophysicist. I'm here.
Oh, you're not talking to me. Okay, fine. I'll go read a book.
You guys are awesome to have on here. I love the way that you guys are together. It just makes it so much fun. This
is sort of out of my league. But I have read that gold has the color that it has, and that was the first clue that the atomic physicists sort of got on this. Is that gold's color doesn't make sense based on what used to be the standard model of atomic orbits. And it's because that outer orbit of that electron in gold is so massive that outer orbit, it's actually going faster to have relativistic effects on its absorption energy when it absorbs photons out of the environment. Wow. And so it gives it a different color than what they were predicting when they first looked at that.
Wow.
So it's a quantum mechanical effect.
That sounds really cool.
Yeah, it's a quantum mechanical and relativistic effect seen in the macro world, because it actually changes the color of gold to be that yellow color instead of the standard silvery color that most metals are.
Wow, that's crazy. I never thought about why it was gold. It's just gold. So wow, I didn't even.
Copper.
What was that?
What's the deal with copper?
Hell if I know, dude. I told you I was talking out of my area. I don't know.
He started off with saying this is out of his field. Oh my goodness, y'all are too much. Okay, I'm gonna give this one. I know we're over time, but Kat, I'm gonna give it to you. Your last one. She brought it all the way back to Mars. There are certain specific time opportunities to land on Mars. Do you know what they are?
Yes. This goes back to, I mean, I don't know what, I could look them up, right? Or I could calculate them if you gave me enough time, but it's something I could tell you if you gave me enough time to sit here and calculate it and figure out where the orbit of Mars is right now. But this goes back to the discussion about the Voyager. Now, you guys aren't old enough to remember, but I remember they actually had a cow over the fact that people were talking about delaying the launch of Voyager back in 77, I think it was, because they were going to miss that window where they could use that slingshot effect off of each planet as they went further and further out. And it was like once in 100 years that all of those planets lined up. And they weren't truly in a line. They were just, one was far enough behind the other one that by the time it got to the next planet, they were going to intercept. And so if you just look, none of the planets seemed all that, in conjunction or anything. But astronomically or in terms of space travel, it was the perfect window in time to launch the thing. And it's like, if you don't get the rocket ready and fueled up and the probe on the, on the nose of the rocket, then we're screwed here because it's not going to get the boost it needs to go to the outer planets.
Now, when was that?
Late 70s.
Wait, I think he froze.
So Voyager 1 and Voyager 2, if I recall correctly, Voyager 2 actually launched before Voyager 1. But I think they both launched in like 77 or something.
I think it was 77 if I remember right.
Okay. I was just curious about that.
And one of them went to the two ice giants as well. Like, I don't know if I don't remember which one went where, but do you?
One of them, and I'm not exactly sure what the logic or the rationale behind that was, but I think one of them diverted at Saturn and went out of the solar plane.
Yeah.
And the other one, Voyager 2, I think, kept going.
Yeah.
So it went on to Uranus and Neptune.
Okay.
I Googled it. It's about once every 26 months that the Mars transfer orbit, opening or window, whatever it's called. According to a quick Google, it's around every 26 months for Earth just to Mars. If you also then want to leapfrog and do other things, then you have to wait kind of for all of those to line up, which is
they all have to be in sync in some way that makes it work.
It depends on how much fuel you have, because if you have a bunch of fuel, then those windows get wider because you can sort of accelerate and make up the difference.
Sure.
But then you're just
if you have enough fuel, you don't care at all. You'll just get fly direct,
All right, so we have gone over, and I want to thank you both for allowing us to go over because I loved this conversation, and I actually didn't want it to end. I've had so much fun tonight. I want to thank everyone.
You do it every time. I mean, it's not like it's ending.
I want to thank everyone in the chat because y'all were a lot of fun too, and we're throwing things out. It was just fantastic. Thank you guys so much. Put some of those comments in the chat afterwards because that always helps us. We like it when there's comments in the chat after. So I'd like to know from both of you before you leave, what is the one thing that you want us to take away from this discussion about space travel? Or about any of the other things that we talked about?
Space travel or space colonization? You're talking about actually carrying humans?
It doesn't matter. You pick whatever you want us to take, because we went in so many different places that were fantastic. So what?
Well, my message is simple. It's like be patient. It feels like it's glacially slow, But at the same token, I say all the time that I never thought I'd live to see a rocket fall out of the sky and land on its ass. And so there's a lot of steps here, hundreds, thousands of steps that we have to make. So it feels like it's going to take a long time, but one day you'll wake up and it will have just happened if you live long enough, and it can happen over the course of a lifetime. So I had some. This is the fun part of getting old. I had some cool thought I wanted to share, and it's gone right out of my head. I forgot what it was. So I'll let Vandy talk, and I'll interrupt him halfway through what he's saying.
Well, on that sort of idea, there are a lot of people out there, none of which are still alive. But if we went back 10 years, there would have been a few that were still alive, that were born before heavier than air flight was invented and died, or were still alive, after we landed on the moon. Like, that is 1903 to 1969. That's crazy fast.
Something I never thought of. Oh, sorry, you weren't done. I told you I'd interrupt you.
Yeah.
Something that I didn't think. I was watching Eric Weinstein the other night, if you know who he is. But he made the point that there were people that lived and fought in the Civil War that saw Hiroshima and Nagasaki take place. Yeah. By the way, the cool thing that I couldn't remember a minute ago, there's a rocket launch every other day. I mean, people don't even realize it, but if you watch the streaming videos on YouTube and stuff, and when they come up, we're literally sending rockets up every other day. It's become mundane.
Mm-hmm. Landing on its ass has become mundane. They're reusing some of those. Some of those are on their like 20th, 30th reuse. That's
really part of the deal is we're getting a launch every other day because they're being recyclable now. It's not like getting shot off and it's just gone once you've shot it. So it is, that's the way progress works. I mean, you guys probably are old enough to remember when we didn't have an internet and we take it for granted.
Oh my gosh. I was just saying the other day, I remember being told about the World Wide Web, and it freaked me out because all I could think of is a big spider. I could not figure out what this was, this World Wide Web. And in my brain, it was a big web with a huge ass spider. And it freaked me out. But they said it was going to change everything. And I'm like, how is this going to... It didn't make any sense. And then I remember whenever it finally did come out and people were just starting to use it, when, the AOL dial-up sound was what you heard. And, and that was if you were lucky to be able to have that. That I remember some of the people saying that was the beginning of the Mark of the Beast, and, the beginning of all the... getting it is going to be the beginning of the end and everything.
Well, maybe they're right. I mean, I can remember when the internet came out, and I was talking to a friend. I was eating lunch with a friend, and I'm going, you realize how huge this is? It's like some kid can be born in Rwanda. He can be the next Einstein. And he's not limited by the fact that he doesn't have a public library right down the road. He can get on the internet and he can learn anything he wants to learn and realize whatever potential he's got, regardless of where he was born. That's friggin' huge. And of course, I was all excited. This would have been, I'm going to guess, right around 2000, right around the turn of the century. I was all excited about it. And then we used it to look at cat pictures and get into political arguments all the time. So, I mean, hopefully the kid in Rwanda can still do that. If that actually happens, but who the hell knows?
Yep. Well, I have one last question I'm going to have to ask, and then I promise we will stop. But Wes just asked a really darn good question. What are we going to do about space trash?
There is no space trash. If we do this is recycling to the next level. We're talking about drinking your pee here. It's like that's going to happen. whatever you've got with you is more precious to you than anything else you're going to come across as you in your travels.
Well, what about discarded chunks of stuff that remain in orbit, or satellites that go offline that aren't properly deorbited? I think that like space traffic it might be a better sort of.
Oh, I thought we were still talking about space travel into deep space, but yeah, okay.
I think
satellites
yeah,
and that's
a problem.
I vacillate on that one. I mean, space is awfully large out there, and it's hard for me to believe this one nut can hit the International Space Station, and then everything just chain reacts, and it's all just a big cloud of mess that we can't get out of anymore.
Mm-hmm.
But I guess that's a possibility. I mean, it seems extreme, but we happened
once.
Pardon me?
There was a collision between like a telecom satellite and like a defunct Russian military satellite. They actually collided, and it happened in the same month as two like secret, like a U.S. and a Russian sub ran into each other, and which is silly for other reasons, and it caused all this debris. And it's a big problem. It's actually like the debris field from that particular collision is one of the larger, like well characterized and known debris fields in low Earth orbit that they still like try and track. But you have to track things down to small, like if it's more than 10 cubic millimeters. It has the potential to do a lot of damage. If it's like 1 cubic millimeter, you can design things that are able to take that without being destroyed. Like little flecks of paint and stuff, those hit the ISS all the time. The astronauts described that if they just close their eyes and listen, they can hear the occasional speck of dust or whatever.
Yep. Well, escape velocity is 11 kilometers per second, if I remember right.
I don't remember.
At 3 kilometers per second, the kinetic energy of an object moving at 3 kilometers per second is going to hit you with the same wallop as if you detonated that much TNT of the same weight. So, yeah, I mean, there's stuff flying around at relative velocities here that are easily 3 kilometers per second or 10 kilometers per second, or if they're going in opposite directions, even beyond 11 kilometers per second. So you're talking about, this thing detonating, and if it hits something, with more than its weight, 3 or 4 times its own weight, like it was TNT going on. So
that's crazy.
That's why I vacillate. That's why I say, wow, there's a lot of space out there, and I can't believe you got to be that worried about running into something. But you do run into something, it's going to be bad.
And it could get a chain reaction, because if that happens to a large object and that large object is disintegrated, suddenly you have literally 100 times more debris to worry about, and then you can get a chain reaction.
It's a critical mass thing, right? It's like when you get enough of that stuff up there and enough collisions happening, it's just a matter of time before they all start bouncing off of each other.
There is one saving grace, which is that the area where this is the biggest problem is low Earth orbit, and atmospheric drag does operate to clean up some of this on long enough timescales. So after 50 years, a lot of that debris will have actually deorbited on its own.
I do remember a story where the astronomers saw this anomaly, and they were like, "What the hell is that thing?" And they thought it was a near-Earth asteroid that had been captured, by the Earth, and had actually come into some sort of stable orbit around the Earth. And they finally got a good enough picture of it. It's like, it's white. Why the hell would it be white? It was the second stage of one of the Apollo rockets that was still in orbit, just floating out there in space. I mean, that thing's monstrously huge. That thing was probably 100 feet long.
Yeah.
And so, yeah, something like that runs into your space station, you're going to have a bad time.
Really bad
and something
time.
like that will stay up there for longer because drag more efficiently moves smaller things because it's a square cube thing.
Yep.
Surface area versus, yeah.
Well, I want to thank you guys so much for this conversation. We went into so many different areas, and it was definitely not the conversation I thought we were going to have, but I think it was far better.
We always do that. We always go off on tangents that we barely scratch the surface of what we said we were going to talk about.
I feel like we actually stayed on task very well this time. This felt like one of the more coherent conversations.
I was about to say for us, yes, relatively speaking, we actually did really well tonight.
We did, but it's always a good time though. We have a good time, and I think that our viewers enjoy it too. So I really do appreciate you guys coming on. Thank you so much.
One of these nights I won't be teaching at night anymore, and I'll be half drunk when we do it. I'll be at home drunk.
We could do, you've heard of a drunk Shakespeare? We could do drunk Sunny Spot.
There you go.
Well, if you guys enjoyed it as much as we do, keep in mind there's several ways that you can help our channel, because we have a lot of really good channels, or stations on our channel. But one thing you can do that's really simple and easy is to like, subscribe, share this, chat in the comments after the show. All of those things make a big difference and help the algorithms, and they're interesting beasts that they are. But if you really want to try to help us out, consider being a patron. Our current patrons are Paul Cammish, Puck, Kellen Green, Logan Fisher, Amanda McLeod, Eric Ozols, Rion, Deneen Murphy, Dandy, Michael Wiseman, me, Aaron Coalson, and Phil Calderone. We want to thank all of you guys who keep our lights on. We really appreciate you. We also have some other shows that you can check out on Skeptic Haven. Tuesdays, we have Secular Soapbox. Of course, Thursdays are here with me with Sunny Spot. Saturdays, we have 2 shows, The Global Atheist and Women Atheist Unload. And then on Sunday, we have Let's Talk, which is our call-in show. So you can call in and talk to us, and we talk to you and answer all kinds of cool questions and have interesting discussions. In the meantime, if you think that you might want to volunteer, we definitely have some volunteer needs that we would love for you. If you are thinking about it, just let us know. You can pop into the chat and let us know. You can also send us an email, all different kinds of things. I think right now it's wesdsturdivant@gmail. Is that right, Wes? I think it is. And we're going to be changing up some of that, but for right now, we're keeping that the same.
Skeptic Haven. Oh, sorry. Skeptic Haven at gmail.org, I believe.
Thank you. It was the voice. The voice from the nether regions that just thank you.
Oh, you guys are hearing that too. Okay. I thought it was like the 3 voices I heard earlier. But no,
I have so many I don't even react anymore.
Thank you very much, Kat. That was awesome for you to do that. Anyway, in the meantime, remember to always think critically. Good night, everybody.
Part of our being knows this is where we came from. We long to return. And we can, because the cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself. If we are not able to ask skeptical questions, to interrogate those who tell us that something is true, to be skeptical of those in authority, then we're up for grabs for the next charlatan, political, or